Hello everyone. Today we're going to look at equations with radicals. I'd like you to try the following problem that I'm going to post on the Do Now. Solve for x in simplest form in the set of real numbers. And the equation is x times the square root of 2 equals 18. Okay, take a minute and do that. Okay, so to solve this, we divide each side by the square root of 2. Since it is the coefficient of the x, we get x is 18 over the square root of 2, but this is not in simplest form since there's a radical in the denominator, so we rationalize the denominator by multiplying the top and bottom by root 2 over root 2. So our answer is x equals 18 times the square root of 2 over 2, which is 9 root 2. And that would be our answer in simplest form. Okay, so I'd like you to try these yourselves. Number 2, I'm going to change the variable x times the square root of 3 equals 2 times the square root of 6 minus x times the square root of 3. That's 1. The next one is 3 x times the square root of 6 equals x times the square root of 2 plus 4. Okay, let's try these. Take a minute, copy them, and think about them. Okay, so to solve the second one, the idea is that in algebra, if we ever want to solve for the variable, anything attached to the variable should go on the same side. So in this problem, in number 2, we will add x root 3 on each side. And we get, because these are like radicals, we'll get 2x times the square root of 3 equals 2 root 6. Now it's a little strange, but the coefficient of x here is 2 root 3. So because 2 root 3, I'll rewrite it this way, 2 root 3x, and multiplication's commutative, so I could always rearrange the numbers. We divide both sides by 2 root 3. And we get x equals, now the 2's drop out, and we get root 6 over root 3. And there are lots of ways to simplify that. We can rationalize the denominator by multiplying the top and bottom by root 3 over root 3, in which case we get root 18 over root 3. And, I'm sorry, I meant root 18 over 3. Let me just write that down. And the root 18 can be simplified into root 9 times root 2 over root 3, over 3, I should say. And that gives you, that gives you 3 root 2 over 3, which is just root 2. An easier way to simplify this is to use one of those properties of square roots. We could put this all under one radical, and since 3 goes into 6, we just get root 2, which is so much faster than rationalizing the denominator. Okay, now in number 3, we do the same thing. We want to bring all the expressions with x on one side. So we subtract x root 2 on each side. And here we cannot combine the radicals. So we write x root 6 minus x root 2 equals 4. Now to get the x to appear once, what we'll do is we'll factor it out. It is a common factor to these two terms that are being subtracted. And we get root 6 minus root 2 equals 4. We divide each side by this coefficient, and it's a strange coefficient for x, but that's the coefficient. And we get x equals 4 over root 6 minus root 2. Now, this is a binomial denominator, and we do have a radical. And to simplify it, we multiply the top and bottom by the conjugate. And we're left with 4x equals 4 times root 6 plus root 2. And then the bottom is the difference of two squares. We can multiply it. So it's root 6 squared, which is 6, minus root 2 squared, which is 2. This gives us 4. And that divides through with the 4 on top. So our answer for that problem is root 6 plus, oh, I forgot my root 2 here, plus root 2. And the solution set is an irrational number, but that is the solution set in the set of real numbers. Now, so I wanted to show you a few equations that involve radicals where we have to simplify the answer somehow. And I wanted you to try this one. Okay, so this is number 4. Okay, and that is 20 plus x root 5 equals 3x. So take a minute, copy it, try it, simplify your answer, and we'll go over it. Okay, I've written out the solution for you. The first step is to subtract each side by x root 5 so we could bring the x over to the right side. Then we factor out the x in this side to isolate it. We divide each side by the coefficient of x, which is 3 minus root 5. And we rationalize the binomial denominator by multiplying by the conjugate. Here's the conjugate. And I didn't multiply the top out, but the denominator is multiplied to 3 squared, which is 9, minus root 5 squared, which is 5, to here. And that gives us 4. The 4 divides into the 25 times, so the answer for x is 5 times 3 plus root 5, or we could write it as 15 plus 5 root 5. Either one is acceptable. So let's just put a box around our answers there. Okay, so that takes care of the radicals in equations, but notice that in all of these equations, the radical part, the square roots, were within the equation, the square root of a number. All right, since we're on radical equation, let's move on to the next page. And I'd like to show you this problem that I gave as an extra credit previously. And that is the square root of 42 plus the square root of 42 plus the square root of 42 plus, etc. Okay, this is a very nice problem, and we are all able to do this. First, let's take a look at the calculator. So to investigate this nested radical that goes on infinitely, let's use our calculator. So I'm going to type in the square root of 42, start with that, and we'll get the decimal approximation for it. And here we go. Now, what we want to do is add 42 and take the square root of that. So I'll begin by doing control square root symbol, which is right under the square. I'll type in 42. And then instead of retyping plus the square root of 42, I'll just put the plus there. I'm going to go up, highlight the square root of 42, and press enter. So now I have nested radicals, and I have control enter, and I get 6.96. All right, I'll do this a few more times. So I'll put my square root symbol, put the 42 plus, go up and highlight, press enter, and then have the calculator do the work. I get 6.997. So we see that this number is increasing. Let's see now if we do this a few more times. Let's see. So control square root 42 plus enter. And now let's see what we get. So we see that this is slightly increasing, not as quickly as the others, but slightly increasing in the tenth, the tenth, hundredths, thousandths place. All right, let's do this one more time. Control square root 42 plus, and then I go up to the previous one, enter. Now I think this should do it. Control enter. Oh my gosh. Now we go to the 10,000th place, and that's increasing. One more time. So we have control 42 plus, go up and highlight, enter, control enter. Now notice that the approximation is really very close to 7. And this is an example in calculus called a series, and it's a series of partial sums. Notice how we keep adding the square root of 42. And we see that the sequence or the list of partial sums seem to be getting closer and closer to this number 7. And if we continue, we would probably keep getting 7. And let's just do that to convince you. I'll do it one more time. Control square root 42 plus. Go up and highlight, press enter. And now I would suspect that we get 7 again. Yes. So the answer to this infinite sum is 7. Now we're going to prove it algebraically. Okay, so to solve this equation, we set it equal to x. Let x equal the number. Now, to undo a radical sign, what we'll do is we'll square each side. So I will rewrite this. And we'll square this side and this side. Okay, now when we do that, this top radical symbol will disappear. So we get 42 plus the square root of 42 plus the square root of 42 plus the square root of 42. So remember, this is an infinite sum. Goes on forever. But if you look at it carefully, this is x. It's still the infinite sum. And we get 42. We replace this with x. And now we have a quadratic equation to solve. So we bring all the terms on one side. We'll subtract the x. We'll subtract the 42. And we'll factor this. So two factors of 42 that are one away from each other are 7 and 6. But because this term is negative, the 7 should be negative, and the 6 is positive. So we have x minus 7 equals 0, or x plus 6 equals 0. So x is either 7 or x is negative 6. Now we've got two possibilities. Which possibility should it be? Well, we know the answer is 7 from the calculator. Here we reject it because, as we said, the square root of a number is always understood to be the positive root or the principal root. So we reject negative 6, and therefore x is 7. And that would be a nice little way to prove the answer. Okay, let's try a few. Okay, so I've written the next two problems. I'd like you to copy them into your notebooks and pause the button and try them yourselves. Okay, so I've written out the problems for you. Number 6 is just like the previous problem. We have the square root of 30 plus the square root of 30 plus the square root of 30, etc. We set it equal to x. We square each side. We square each side here. Notice that this top radical disappears, this one here. And we're back to x here. And we solve the quadratic equation. We get x squared minus x minus 30 equals 0. We factor it into x minus 6 times x plus 5, set each factor to 0. We get 6 or negative 5. And of course, we reject the negative 5, so the answer is 6. Now, in number 7, this one's a little different because we're not adding. We are taking nested square roots, but the product of nested square roots. And notice that these numbers alternate. So we proceed in the same way. We set it equal to x. We square each side, and that gets rid of this top radical symbol here. Then, to get back to the original x, we'll square each side again. But here, this radical symbol will disappear, and we have to square the 8 because we have a product. So when we square each side again in the next line, the top radical disappears, and I get the 27, and we square the 8 because it's the square of a product. Notice I didn't multiply this 64 by 27, and you'll see why in a minute. So this expression gives back x, and we bring that over to one side and factor it. We get x times x cubed minus 64 times 27 equals 0. We factor out an x. It's not a quadratic. X has to be 0, which we reject. Of course, this is not equal to 0. So the x cubed minus 64 times 27 equals 0, which means we get the x cubed equals 64 times 27. When we take the cubed root of each side, notice I factored the 64 and the 27 into 4 cubed times 3 cubed, and it's so much easier to take the nth root of any number as long as it's factored in with its as much as possible. And we get that the final answer is that x is just 4 times 3, or x is 12. And that would complete the next problem. Now I'd like you to try these for extra credit. These problems are a little different, but I'm sure you'll be able to do them in the same way. They may require the quadratic formula when you get to the quadratic equation. Okay, so for extra credit, I'd like you to try these. I'm messing up my extra credit here. Okay, so for extra credit, I'd like you to try these. They're a little different. The square root of 2 minus the square root of 2 plus the square root of 2 minus the square root of 2 plus the square root of 2 minus etc. So these are nested radicals, except what's different about this is that the signs alternate. So see what happens there. You may need the quadratic formula. Another one which I found very interesting was this one. Okay, I'll turn back to black. It was the square root of 2 plus 3 times the square root of 2 plus 3 times the square root of 2 plus 3 times the square root, and this repeats in that pattern. Now this one, we do the same way. You may have to square each side more than twice, but see what you can do with that one. Okay, so I think those are the two that I wanted to show you. There was Ramanujan, who was a very famous Indian mathematician, came up with this problem. Now, we won't be able to do it using quadratic equations, but you can, I would suggest doing this problem by looking at the simple cases and taking it case by case and make a conjecture. His problem, he posted in a journal one time, and no one came up with the answer. He said it was 1 plus 2 times the square root of 1 plus 3 times the square root of 1 plus 4 times the square root of 1 plus 5 times the square root of, etc. 6 times the square root of dot, 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 dot. Okay, notice that here, these numbers are increasing. So this one cannot be done algebraically, but I think the best way to approach it is taking a look at the simple cases and keep adding it to it, similar to what we've done with the calculator. And you'll come up with a conjecture, and I challenge you to write a convincing algebraic argument of what the answer should be. Okay, everyone, that takes care of this lesson. I hope you have a wonderful day and take care of yourselves. Bye.